On the urinary system. Yeah. You have a lab exam on Tuesday, and we'll go ahead and start digestive lecture after the lab exam. I have the lecture notes delivered already. But remember, your exam is not due until next week. More time.
It's Friday night.
Saturday night. Well, I mean, you can turn it in class on Friday. Still need to work. So when we look at acid-base balance, we've already talked about acid-base a bit when we talked about the respiratory system. And we looked at the interaction between carbon dioxide and water. We talked about the difference between a weak acid and a strong acid, and the fact that hydrochloric acid is considered to be a strong acid, even though both carbonic acid and hydrochloric acid give off a single hydrogen ion when they dissociate. More of the hydrochloric acid ions are going to be dissociated than the carbonic acid, right? So we end up with a greater number of free hydrogen ions. For it to affect pH, it has to be a free hydrogen ion. So if it's bound to the bicarbonate ion, or if it's bound to the chloride, then it's not a free hydrogen and it's not going to affect pH. Okay? So as we look at the body's systems of buffering, that's how we buffer the pH. Is we release a free hydrogen ion, or we take up a free hydrogen ion, or you can do similar aspects with the bicarbs to adjust that level. So most of you are familiar. If you're not, you can go back to early chapters in your textbook. But pH is related to the concentration of hydrogen ions. All right, so pH goes down as hydrogen ion concentration goes up. And it's a logarithmic relationship. So if we go from a pH of 5 to a pH of 4, we have a 10-fold increase in the number of hydrogen ions. Right? And then if we drop down to a pH of 3, it's 10 times that, so that would be a 100-fold increase of the number of hydrogen ions that we have in a pH of 5. So it gives us a manageable way of dealing with these huge numbers. And we talk about that logarithm. So as we move into this, what are some of the mechanisms or some of the processes by which we change, add hydrogen ions or add bicarbonate ions to the body? Pardon? Breathing, okay? So that's what we've covered in our previous unit. So anything that is going to increase carbon dioxide in the blood because of our carbonic acid relationship that we already talked about, we get carbonic acid, which can further dissociate to hydrogen ions, bicarbonate. You might say, well, there's a bicarbonate ion, so why doesn't that just buffer the hydrogen ion? Okay? And it can, but remember, these are concentration driven. So if we have a lot of CO2, we're going to end up with a lot of carbonic acid and a lot of hydrogen ions. If we don't have very much CO2, then the chemical reaction is going to be driven in the opposite direction. So this is one way in which we can increase or decrease our hydrogen ions in a respiratory fashion. All right? So by changing our respiratory rate, increasing or decreasing our breathing rate, can increase or decrease our carbon dioxide. What about, and so that's considered to be the respiratory component of the equation of acid-base balance, and even one of our buffering systems. What other sources do we have for hydrogen ions in the body? Amino acids. And amino acids as proteins can actually function as part of a buffer that we'll look at in just a moment. So amino acids have a nitrogenous group and an acid group and something else here. Actually, that should be a C here. And an R up here. Am I doing that right?
Yep.
Okay. So we can change these hydrogens here by adding an additional hydrogen here. So if we change this hydrogen, then we have an extra charge. Or, when we look at this as a buffer, this hydrogen can be released, and we can add an additional hydrogen. Okay, so depending on the pH in the body, different amino acids will either bind that hydrogen or release the hydrogen. As we break down amino acids then, through exercise or through fuel use, we can adjust the amino acids or change the number of the amino acids in the body. What about just pure hydrogen ions? So as a hydrochloric acid, the stomach produces this as a mechanism for activating enzymes in the gastric cavity. And so as these are reabsorbed or are taken back up across the digestive wall, then we're going to increase hydrogen ions. Okay? So we'll see this as a source of metabolic changes in pH. If someone is throwing up extensively, pregnancy or a stomach flu or whatever, then we do not reabsorb these free hydrogen ions, and the body can have its pH raised too high because it has insufficient hydrogen ions. How do we normally, does anybody know, we haven't done digestive system yet, does anybody know how we normally buffer these absorbed hydrogen ions? What's the other organ in the body? So our source of hydrochloric acid is going to be the stomach. Our source of bicarbonate ions is the pancreas. So enzymes produced by the small intestine require an elevated pH, an alkaline pH of around 8 to 9. The food that's coming into the small intestine from the stomach is going to be a pH of around 2, 1 to 2. For some reason, I have no idea why our body does it. Acid in the stomach and alkaline in the small intestine, but now we have to neutralize that acidic pH of the chyme coming in. That's what the processed churned up food in the stomach. And so the pancreas, along with digestive enzymes, makes a lot of bicarbonate ions. So those are absorbed across the digestive wall of the small intestine, primarily the ileum, and will help to buffer these hydrogens. So if we have a lot of diarrhea and we lose the bicarbonate ions, then we lose that buffering capability for the hydrogen ions. Right? In addition to processing proteins and gaining amino acids, the body goes into starvation or eats a low carbohydrate diet, high fat diet, depending on what the person is trying to do. You can increase lipid digestion and increase fatty acids. So somebody who is a diabetic and is not well regulated with their diabetes can go into ketoacidosis, and that's a low pH due to elevated fatty acids. All right, so we have a lot of other metabolic sources of hydrogens or bicarbs other than the respiratory system.
Fatty acids would increase or decrease pH?
Fatty acids would lower pH by increasing hydrogen ion concentration. So up at the top of the screen here, and we're in this balance of light, and it may be a little difficult to see, but with homeostasis, we normally have a pH range of 7.35 to 7.45. And that averages out to a pH of about 7.4, so slightly, just very slightly on the alkaline. When we have a pH of that range, we typically have our carbon dioxide in the blood range. If you recall, in the arterial end, it's a PCO2 of 40, and in the venous end, it's a PCO2 of 45. So we're in this range of our carbon dioxide, we're in our normal pH range. So you can see that if we have some problem with gas exchange, so the CO2 builds up in the body. As CO2 builds up, carbon dioxide forms, and we go into respiratory acidosis. Okay. And reverse, if we hyperventilate and PCO2 falls, then we go into respiratory alkalosis. So towards the end of today, we're going to talk about some of the differences between respiratory versus metabolic acidosis and alkalosis. So with all of these changes in the body that can affect pH, we look at buffer systems. Now, a buffer mechanism is most effective when it can be modifying both acid and basic or alkaline conditions. So your most effective buffer can respond to a change in pH by either accepting a hydrogen ion or giving off a hydrogen ion. Okay? So in the example that I gave you here of an amino acid or protein, amino acid component of a protein, the ammonia group could accept a hydrogen ion. So if you have this molecule in a low pH situation where there are a lot of hydrogen ions, what would you expect to see it look like? So there's lots of free hydrogen ions around. The body fluids are in an acidic condition. Would we have a free hydrogen ion over here? No. So this hydrogen ion would come back to the acid, and instead we would take one of these hydrogen ions and add it to our ammonia group. Okay? If now we are in a basic situation where we have insufficient numbers of hydrogen ions, then this would act as a buffer. We certainly wouldn't have this one here. This would act as a buffer, and we would release a free hydrogen ion to lower the pH by elevating the number of hydrogen ions. So a buffer then functions in either direction. So it will accept a hydrogen ion, or it will release a hydrogen ion along that pattern. So typically when we look at molecules that function as a buffer, they are a weak acid or a weak base. Why does it have to be weak?
You don't want to dissociate.
If it was a strong acid like hydrochloric acid, it would never accept the hydrogen. It would always release the hydrogen ion. Okay? So on the screen here, you can see several different components or systems that we use to buffer. Some are chemical buffers, right? So we have a phosphate buffer. We have proteins, which is like a hemoglobin molecule would be a buffer. And we have our carbonic acid bicarbonate buffer system. This is not the same as respiratory organs. So many of the time students think, oh, carbonic acid, that's the respiratory system because the two are so closely linked. But this, we can get carbonic acid bicarbonate ions from the pancreas. So that's looking at the chemical nature of the buffer. All right, and we'll look at some of the examples. But then we have whole systems where the respiratory buffering system is actually breathing off the CO2 or holding the CO2. That's what we mean by the respiratory system as a buffering system. And we'll come back to our urinary system when we talk about the urinary system as secreting hydrogen ions, reabsorbing bicarbonate ions, or secreting bicarbonate ions. So actual movement of the ion rather than chemically binding it to one source or another. So here's what I drew on the board over here as an example of a protein buffering system. So we have the amino acid, all right, and when we need additional hydrogen ions, the hydrogen comes off of our carboxyl group there. And if we have too many hydrogen ions, then we replace that and add an additional hydrogen ion to the nitrogen group. You're familiar with the carbonic acid, right? So when we have accepted the hydrogen ion, so if we have too many hydrogen ions and we've accepted the hydrogen ion, then we have it as carbonic acid. That would be the form that you would expect to see this buffer in an acidic solution. If we were in an alkaline solution, you would see it in this form as a bicarbonate ion, where it's given off the hydrogen. Okay?
Isn't there a point it'll lose that second hydrogen?
This one here,
Uh-huh.
that'd have to be really, really high.
I thought it only had to be 12s.
But body-wise,
Yeah, it is pretty high for the body.
you have other problems going on by. I mean, I'm sure chemically you could create a solution where that would happen, yeah. All right, and so when we look at, so those are chemical systems, and another chemical system is the phosphate system here. We're going to come back and look at the bicarbonate ion system here. But I'm mentioning the phosphate system here. Although we said that phosphate ions were intracellular ions yesterday, it was one of the ions that were high levels intracellularly, it is one of the key buffering systems in urine filtrate. So all three are shown here: carbonic acid bicarbonate, the phosphate buffer system, and the ammonia buffer system. These are buffering within the filtrate. So why is that important that we have these buffering systems in the filtrate? Obviously, protein is not going to be a buffer system in the filtrate. Why is that obvious, or should be obvious at least? Because proteins should not be present in the filtrate, okay? So proteins are an important buffer in the blood, intracellular, but in the filtrate, they're not available. So why is it important that we have buffer systems? And we have these other buffer systems since we can't have protein. So if we're using the urinary system, remember with the respiratory system, we don't directly breathe off hydrogen ions. We breathe off CO2, which means we form less carbonic acid, but we don't directly move hydrogen ions out when we breathe. With the urinary system, we do, all right? So we would move hydrogen ions into the filtrate. What's that going to do to the pH of our filtrate?
It's a little lower.
It's going to really lower it, and you can imagine how much it would burn if you were excreting a urine with a pH of 1 or 2. All you have to do is throw up a few times in the burning acidic nature of that, so that would be really uncomfortable. And so these buffering systems within the filtrate take out the free hydrogen by binding, and they'll take it out of the filtrate, but they bind it so it's no longer a free hydrogen, and now we can add additional hydrogen ions to the filtrate. Okay? So if we did not have a buffering system, that would limit the number of free hydrogen ions that can be moved out of the blood and into the filtrate. With the presence of a buffer, those free hydrogen ions are now bound to a bicarbonate ion, or they're bound to a phosphate or to ammonia group, and now additional hydrogen ions can be moved into solution. Okay? We're going to focus primarily on the carbonic acid bicarbonate system, but so hydrogens can bind to bicarbonate or carbonic acid, hydrogens can bind to the phosphate ion or biphosphate here, or to the ammonium ion. So I want you to recognize those as the three buffering systems, with phosphate being unique. We don't normally see that in other locations. So I told you when we talked about the proximal convoluted tubule that we were going to talk about secretion and reabsorption of hydrogen ions. So I'm going to turn the screen off here. You have a diagram. Essentially what I'm going to diagram is this, without the sodium ATPase, is this sequence right here. We have the so we have 2.5 different locations where we modify hydrogen bicarbonate ions. I'm going to just make that as a part of it. We have the proximal convoluted tubule. And in the distal convoluted tubule and collecting duct, we have intercalated cells. Type A. What these cells do is they secrete hydrogen ions and reabsorb bicarbonate ions.
On both or just the?
Both of them. Okay. The intercalated cells type B we do the reverse. They're going to secrete bicarbonate ions and reabsorb hydrogen. But this is primarily what the urinary system is known for. So would the body be in acidosis or alkalosis for this to happen? Which direction when we talk about secretion are we moving?
Oh.
The blood secretes.
Blood to filtrate or filtrate to blood?
Blood to filtrate.
Blood to filtrate. So if we're secreting hydrogen ions from blood to filtrate,
It
we
decreases.
would be doing that with a low pH of acidosis or a high pH of alkalosis.
In the blood or in the
Low
wait,
pH.
where?
Acidosis.
All right, so when we have acidosis, all right, acidosis is considered to be a pH of below 7.35. As we lower the pH, what do we do to the number of hydrogen ions? They increase. So if we're getting rid of hydrogen ions, we must have too many.
In the blood.
Therefore, we would be in acidosis.
And that's referring to the blood, right? The blood.
Referring to the blood. Okay? All right, so if we are in alkalosis, we don't reverse this up here, we just slow down or stop it as far as the proximal convoluted tube is concerned. And then to a minor degree, we would start activating the intercalated cells type B. So let's go back to the diagram of the proximal convoluted tubule cell. And because of its extensive microvilli, it's going to be more effective in doing this than the intercalated cells, just because there are more of them and there's more of the microvilli as well. So we would have our peritubular capillary. Our simple cuboidal cell, either in the proximal convoluted tubule or in the distal, what I'm showing here in the proximal. So the same events would be occurring, and this would be filtrate. So we would already have filtered in the blood, filtered across the Bowman's capsule, we would already have hydrogen ions. And bicarbonate ions. And we would have those in the blood as well. But if the body is in acidosis, all right, it doesn't matter if it's a body cause, metabolic, a systemic cause, such as ketoacidosis, or a respiratory cause, all right, body's in acidosis, so we're going to have lots and lots of hydrogen ions. So we're going to end up in secretion. We're going to move additional hydrogen ions over in this direction, so from blood to filtrate. Is secretion. We want to move hydrogen ions into the filtrate. We've got a problem. Hydrogen ions cannot cross the basolateral membrane of the cell. Hydrogen ions
More complex.
can cross the apical membrane, but they cannot cross the basolateral. So we're back to our old friend. What did we do in the brain when hydrogen ions couldn't get out of the capillary walls of the brain because of the blood-brain barrier.
Carbonic acid.
No, not yet. Before that,
CO2?
CO2. Okay? So as a gas, these molecules will recombine together, form carbonic acid, which will form water and CO2. And CO2, as a gas, can diffuse out of the blood into our cell. Within the cell, it will combine with water. Guess what enzyme we have present in these cells?
Carbonic anhydrase?
Carbonic anhydrase.
Oh.
Now we reform carbonic acid. That dissociates to form hydrogen ions and bicarbonate ions. Bicarbonate ions can move across the basolateral membrane, and the hydrogen ions will be sent out of the apical membrane with secondary active transport. Okay? Either an antiport, often with sodium, but we move hydrogen ions into the filtrate. So now we start adding additional hydrogen ions, and this is where the bicarbonate ions that are already there come into buffer, or the ammonia ions, or the phosphate. So we can take these hydrogen ions, add them to a phosphate, and form as a buffer. Okay. But this is a secretion of hydrogen ions. Now, in addition to that, notice what I said? We can reabsorb bicarbonate. So we can take the bicarbonate that's in the filtrate and send it back to the blood so it can continue to function in the blood as a buffer. So we have the phosphate and the ammonia that we got from our glutamine that can function as a buffer in the filtrate. So we can take this bicarb and send it back to the blood. That's reabsorption. Remember, going from filtrate to blood is reabsorption. However, we have a problem. Bicarbonate ions cannot cross the apical membrane. We know they can cross the basolateral membrane, but they can't cross the apical membrane. So now we just do the reverse. In the filtrate, we take our bicarbonate ion, bless you. Send the carbon dioxide into our cell. It goes through the same reaction with carbonic anhydrase, and the bicarb ion reforms and goes into the blood. So when we start from carbon dioxide from this direction, this occurs with the secretion for the secretion of hydrogen ions. When we start with the carbon dioxide from this direction, this is for bicarbonate ion reabsorption. Yes, Monica?
So it is still called secretion of hydrogen ions, although it's actually
No,
using
it's, well,
CO2. No,
so when we go this direction, so now this is bicarb reabsorption.
Right. But I'm saying from that side, even though what you're putting into the cell is CO2, it's still called secretion of hydrogen ions.
Well, it depends on where we're starting.
Okay.
So if we start with bicarb on this side, we reassociate it with hydrogen ions in the filtrate. So these hydrogen ions were already in the filtrate. We form carbonic acid, dissociate to form CO2. Then we go through this process. The hydrogen ion that's coming back into the filtrate is just replacing the one that was already here.
Okay.
But now we're adding a new bicarb to the blood.
Okay.
Well, it's not a new one, we filtered it, but we're reabsorbing it back into the blood, okay? So this happens at the same time. So now we're lowering, the effect of this is to lower the number of free hydrogen ions in the blood and increase the number of bicarb ions to filter any remaining hydrogen ions that didn't get filtered or secreted. Okay? So this is going to take place when the body is in acidosis. Especially if it's a respiratory caused acidosis, because this is the only way we have of getting rid of hydrogen ions, because there's an interference with the respiratory, the breathing component. And we're increasing the number of hydrogen ions because of that breathing component. This works for both respiratory caused acidosis and metabolic caused acidosis. Okay. So it takes place primarily in the proximal convoluted tubule, but it can also take place in the type A intercalated cells, which are found in the distal convoluted tubule and colectomies. We have a more surface area with all the microvilli that we have there. Again, intercalated type B do the reverse. And that's just because they have the ability of bicarbonate ions can cross the apical membrane. They do an exchange with chloride ions. Yes?
So you only said the bicarb absorption only happens so that we can move out more?
That allows us to buffer. So what we're doing here is we're doubling our effect of raising the pH. We're getting rid of hydrogen ions, physically getting rid of hydrogen ions, and then by reabsorbing bicarb, we're able to buffer more of the hydrogen ions that remain. Okay. So this is showing the type B cell, where this is our blood, this is our filtrate, and bicarb, carbon dioxide comes in, carbonic anhydrase is still present, but in the key thing is the type B cells are permeable to bicarb ions, and they're apical membrane. So there's an antiport exchange with chloride, two negatives are exchanged, and so that's the only cell that we can actually secrete bicarbs. And then, of course, we're reabsorbing hydrogen as we exchange it. All right, so in addition to the buffers, where we either bind a hydrogen ion or release a hydrogen ion, we have the organ systems, the respiratory system, where we breathe off CO2 or we breathe off less CO2 to adjust pH, or the urinary system, where we secrete hydrogen ions and reabsorb bicarb, or the reverse. So those are actually body mechanisms for getting rid of those components. So that leads us then to your lab activity. Over here. Which is on the Henderson-Hasselbalch equation. Anybody seen this before? Besides, okay, so anybody that's in chemistry has seen this before. And I have, this is your extra credit lab on acid base. And there's a worksheet that I'll show you in just a moment that kind of shows you how to go through some of these problems. But I want to focus on this region right here. Okay? So pH is equal to the pK which for our body temperature is 6.1. Anybody know what the definition of pK is? The constant as associated with the dissociation. The pK,
It has to do with the pH, when the pH passes the pK.
it is the pH at which half of the ion is associated and half is dissociated. Okay, so here it's 6.1. It has to do with affinity at that particular pH. So now, that's going to be a constant for our body temperature, because it changes with temperature. So with the standard body temperature, that pK is going to be a 6.1. And notice what we're looking at here, the base over the acid. So the base for our body is the bicarbonate base, and the acid is shown as carbonic acid. However, it's a little difficult when we look at body physiological tests. We don't really measure carbonic acid. What do we have an easy measurement of? PCO2. Right? So instead of using this particular straight equation, we're going to say that pH is equal to the 6.1 plus the log of our bicarbonates divided by PCO2, but we have to modify this because PCO2 is not exactly the same as carbonic acid concentration. So we're going to take the PCO2 and multiply it by 0.03. Normal PCO2 is what? In the arterial blood?
40.
40. Okay. So now if we have 6.1 plus the log, our normal bicarb is about 24 milliequivalents. Okay. And a PCO2 of 40 times 0.03 should come out to a log of 24 over 1.2. What's the ratio of 24 to 1.2? 20 to 1. If you take the log of 20 over 1, anybody know what you get? Right off the bat? You should.
Guessing
What's our normal pH? Our normal body pH is 7.4, right? Halfway between 7.35 and 7.45. So to get that 7.4 as our average normal body pH, the relationship between our bicarbonate ions in the body and our carbon dioxide in the body needs to be a ratio of 20 to 1. A log of 20 to 1 gives us 1.3. We add that to 6.1, we get a pH of 7.4. Now, before we look at some of the problems that you can figure out now with different, in the extra credit, I give you different situations where the PCO2 is high or the bicarb is high. What's the pH? Here's the pH, here's the PCO2, what would the bicarb be, and so on. And it's just a matter of plugging in the numbers. But before we move on to that, I want to show you some situations here that you don't have to do the math to understand what's going on. All right, so let me rewrite that over here where everybody can see it. One is bicarbs, right? One is carbon dioxide. We go a little bit farther in this analogy or problem solving. Bicarbs are a metabolic source. Carbon dioxide is of a respiratory nature. Okay? If we change that normal ratio of 20 to 1, and I change it to a 30 to 1, so what am I increasing? To my bicarbs. Are we going to be in acidosis or alkalosis? I'm going to have too many bicarbonate ions, right? That's our top value. I'm going to have too many bicarbonate ions for the number of carbonic acid molecules I have. So I am going to be in alkalosis. Does that make sense? Yes. Too many bicarbs, not enough hydrogen ions to buffer them. Okay? What's another situation that I can be in alkalosis? I can have a normal number of bicarbs,
0.5.
but not enough hydrogen ions, not enough of our carbonic acid. This is still going to be alkalosis. Does that make sense? Because this is key to understanding how we can see this at a glance of what's going on with the body without actually figuring out the pH. Now, what kinds of things can cause too many bicarbonate ions? That's going to cause breakdown of could be more acidosis.
What's the question?
What kind of things could cause too many bicarbonate ions? Okay, throwing up. Extreme vomiting. Where we have lost the free hydrogen ions from our stomach, so we have too much bicarb from our pancreas. An excessive number of antacids. Those are the most common causes of having too many bicarbonate ions. What would be some common causes of not having enough carbon dioxide? The most common, usually about the only cause, is usually our problem is too much. Hyperventilation, exactly. Notice this is a metabolic cause. This is a respiratory cause. So when this is a number that changes, the condition is described as metabolic alkalosis. We know we're in alkalosis because it's the bicarb number that is out of sync. And we have too many bicarbs for the acid, or not enough acid for the bicarbs. But here we know this is a metabolic cause. This is now a respiratory cause. And I can tell all of that from this ratio without actually going through the math and doing the pH. Okay? Now let's change those values. And let's say that instead of 30 over 1, I have 15 over 1. Normal amount of carbon dioxide, but now I don't have enough bicarbs. My CO2 is normal, but I've lost bicarbs. So in effect, I have too much CO2. So I am in acidosis. Common cause for this is diarrhea. Ketoacidosis, where I've used up my bicarbs because of fatty acid breakdown. My respiratory is fine. I have the normal amount of carbon dioxide, but I don't have enough bicarbs for the acids I've created from fatty acid breakdown. So this is a metabolic acidosis. Okay. Well, now let's say that our bicarbs are normal, but because of emphysema, or pneumonia. I can't breathe off enough CO2. So I have higher the ratio than 1 because I have too much carbon dioxide. So I'm still in acidosis, but now my cause is respiratory. Before you think that this is really easy, here's another situation. They both changed. I have too many bicarbs, and I have too many molecules of carbon dioxide. Okay? First of all, am I in acidosis or alkalosis?
Alkalosis.
I'm in alkalosis. I've increased my number of bicarbs by 50%, but I've only increased my carbon dioxide by 20. You see that? This is half again as much as 20. So the greater increase is the original cause. So I'm in alkalosis. Too many bicarbs. I'm in metabolic alkalosis
Less.
with partial compensation. What does that mean?
Your respiratory system's trying to make up.
Doing what? So my pH is risen. I have too many bike. Let's say I overdosed on Tums. Okay, I went for a bike ride and I started cramping, so I ate half a bottle of Tums. Now my pH is too high.
Your breathing.
What's going to happen to my respiration?
It's going to go down.
It's going to slow down in an attempt to capture carbon dioxide and convert it to carbonic acid to make up for the too many bicarbs I have. So you can see here that my CO2 levels have started to rise. They've gone up 20%. So partial compensation through decreased respiratory rate. Okay. Now, if I had a value of 30 over 1.5, am I in alkalosis or acidosis?
Neither.
Neither. I got a normal pH. Because they both increased by 50%, I don't know which was first. Did I have pneumonia and increase my CO2 and then reabsorbed enough bicarb to buffer that? I don't know which came first. I'm fully compensated because I have a pH of 7.4, a ratio of 20 to 1. So when it's fully compensated, I don't know what the original cause is. Okay? All I know is I have full compensation. Does that make sense? Okay, so you have to, so what you want to do, it's really easy if one of these numbers is the normal value. Okay? You just look at whichever is the change and that's the cause and or the condition. If they both have changed, you need to see which one has changed the most. All right, and the other is a compensation for that. So if my cause is, if I have metabolic acidosis, what would that look like? I'd have less than 20, so maybe 18. Now let's make it a little lower than that. Let's make it 16. To compensate for that, I'm going to increase my breathing. I'm going to start to hyperventilate. And so I will have maybe slightly less PCO2. Okay. So again, without doing the math, you can still look at the ratios and figure out, first of all, is it alkalosis or acidosis? And then is it the metabolic cause or the respiratory cause? If the top value has changed the most, up or down, it's going to be a metabolic cause. If the bottom value has changed the most, again, up or down, it's going to be a respiratory cause. Okay? So on your D2L site is the worksheet to kind of help you go through these problems, because your extra credit has you figuring out, here's the pH, or here's the amount of bicarbs, what is the pH, okay? Let me pull this up here. If you don't have a logarithmic calculator, you can go online. There are free online, just look up logarithmic calculator. And there are free, just punch in the button, the numbers, and it'll click it for you. So here we have, I've given you the conditions. So here is her PCO2. Here are her bicarbs. All right. So just looking at that, without looking at anything else, which one is off?
The
Bicarbs.
bicarb.
The bicarbs, because normal is typically 24 milliequivalents. And so to figure out the equation, we have to convert this to carbonic acid values. So you have to multiply by 0.03. So you do that first before you take the log. All right. Again, this is on D2L, and do the lab part. So you take 38, multiply the 40 by the 0.03, get 1.2. Take 38, divide it by 1.2. Take the log of that value, and 31.67. So I get a value of 1.5. Take that 1.5, add it to 6.1, and I get a pH of 7.6. Okay. Now on that prior website, I just looked at logarithmic calculator, and I can switch it to anti-log. Okay, so for some of these calculations, you need to find the anti-log instead of log. So with this one, you can just switch back and forth.
Is
So
log,
pardon?
is log ln on the calculator still allowed?
No,
What?
yeah, log.
Inverse
LN
one?
is, yeah.
Usually if you want to do the analog, it's the
Inverse
the
one?
function,
Yeah, okay.
inverse function of that.
That allows to just like,
All right, so now with this type of a problem, and I've given you an example of all the things I asked. So with this type of a problem, I've given you the pH is 7.6 and the PCO2. So now what is her bicarb value? Okay. So we're using the same equation, but now instead of log, we need to take the anti-log. Right? So it's going to be the anti-log of the pH minus the pK, and then times 0.03 times the carbon dioxide. So we take the anti-log of 7.6 minus 6.1. We want the anti-log of 1.5. So again, this is all on the D2L. We go back over here, and we want anti-log of 1.5, and that gives us the 31.6. Okay, so even if you don't have a calculator that has the log in the inverse function, I just put in Google the logarithmic calculator, and it was the second thing on the item there. Okay, so if you're not sure about when to use log and when to use anti-log to do that extra credit, This is under the acid-base problem solution guide. And it kind of walks you through examples of each of those steps. Alrighty, we're done.